Welcome back to the Deep Dive. Our mission today is to give you a shortcut into one of the most exciting shifts happening in machine learning architecture, specifically within reinforcement learning, or RL.
For the last decade, we've watched AI reach these incredible new heights just by making models bigger. I mean, you look at the breakthroughs in language like the Llama series or Envision with stable diffusion.
Of course.
We are talking about models built with hundreds of layers. Scaling has been the primary engine of progress.
Absolutely. But in the world of RL, we've been living under this strange architectural restraint.
Hmm.
There's this almost sacred conventional wisdom that says, keep your network shallow.
Right.
Most mainstream RL agents, the ones tackling games or basic robotics, are confined to just 2, maybe 5 layers deep. It's a real paradox, the RL scaling paradox.
Right.
Why does bigger work everywhere else but not here?
And that paradox is exactly what the research you brought us today challenges. We are diving into a deep investigation of scaling network depth in RL, pushing way past 5 layers, past 64, all the way up to 10,024 layers in some of these experiments.
And the central question is whether this vertical scaling, this increased depth, can unlock the same kind of radical performance gains and, I guess, emergent capabilities that we see in the large language models.
And the finding is transformative. It really is. Scaling depth, when you do it correctly with the right algorithms, it drastically boosts performance, sometimes by over 50x in success rate on extremely difficult tasks.
50 times.
And crucially, this scaling leads to the emergence of qualitatively distinct high-level skills. It forces us to just abandon those old, shallow architectural constraints.
Okay, let's unpack this. Why did that constraint exist for so long? I mean, why was it so hard to scale RL networks beyond just a handful of layers?
The core issue is sparse and delayed feedback.
Sparse feedback.
Exactly. Imagine you're trying to train an AI to complete a complex mission. It might take thousands of actions, this long trajectory of observations, before it gets a single bit of useful reward telling it you succeeded or you failed.
So you have this tiny, fragile signal.
A tiny, fragile gradient signal trying to update an enormous number of parameters in a deep network. And previous attempts at scaling depth just failed because that signal vanished. It led to all sorts of training instabilities.
So the key to building a new blueprint wasn't just about more hardware, but fundamentally changing the language the model spoke to itself. How did this research overcome that sparseness?
I used a 3-part blueprint. The first part, which is I think the most critical conceptual shift, was moving away from traditional reward regression and marrying RL with self-supervised learning, or SSL.
Okay.
They used a specific algorithm called Contrastive RL or CRL.
So tell us more about CRL. If you're not regressing to estimate some future value, what are you actually doing?
Well, CRL changes the learning rule from regression to classification, and it does this using what's called the info-NCE objective.
Info-NCE.
Right. So instead of trying to estimate a continuous future value, a number that says, how good is this state, the model learns to classify whether a given state and action belongs to a successful trajectory that reached the goal versus an unsuccessful one.
So you're turning a really difficult continuous prediction problem into a more stable sort of binary choice problem. Why does classification handle depth better?
Because classification provides a dense local gradient signal. Every single time the model makes a classification decision, is this state-action pair good or bad relative to the goal? It gets immediate, robust feedback.
Right. Not at the end of 1,000 steps.
Exactly. And that feedback helps stabilize the gradients through those hundreds of layers. It prevents the vanishing gradient problem that just plagued traditional methods like SAC and TD3 when people tried to scale them up. That's the fundamental algorithmic enabler.
That shift in the objective function sounds monumental. So what were the other building blocks you needed to handle the sheer scale?
The second was leveraging modern GPU acceleration, using these high-throughput frameworks like JAX GCRL to handle the vast amounts of data and compute. And the third was, of course, the deep architecture itself, pushing up to that 1024-layer limit.
But when you're building an RL network with hundreds of layers, you can't just stack them up, right?
Yeah.
You need these structural engineering tricks, things borrowed from deep vision and language models to maintain stability.
Oh, absolutely. We couldn't even have this conversation without talking about residual connections. They're just non-negotiable. They create these shortcut paths that ensure the gradient signal can bypass layers and flow robustly through the entire depth of the network.
That makes sense for ensuring the flow.
Yeah.
But what about managing the data that's actually passing through the layers?
That's where layer normalization became essential. Layer norm prevents what's called internal covariate shift, this really unwelcome phenomenon where the distribution of inputs to a layer keeps changing as parameters update.
Which, in a deep network, would just spiral out of control.
Completely. Gradients explode or vanish. The ablation studies in this research showed that without layer normalization, stable scaling beyond just a few layers was, well, it simply wasn't possible. It keeps the activations well behaved.
And lastly, the choice of activation function. They went with swish over the historically common ReLU.
Correct. The swish function, which is a much smoother activation curve, proved more effective than the sharp cutoff of ReLU for maintaining gradient flow and stability in these models. It just confirms trends we've seen in other deep learning fields.
So we have the stable architecture, the classification-based algorithm. Let's get to the quantitative results because the performance jumps here aren't marginal. They are stunning.
They are exactly what researchers hope for when scaling laws really hold true. Even on standard robotic manipulation tasks, they saw huge improvements, a 2 to 5 times success rate increase over the shallow 4-layer baselines.
But the real payoff, the really eye-popping numbers, were in environments that demand long-term planning and complex spatial reasoning.
Precisely. On challenging long-horizon maze environments, like the AntU4 maze, the deep networks achieved 20, sometimes up to 63 times the gains.
Wow.
And on the humanoid big maze environment, which is notorious for its instability and complexity, the improvement wasn't double or 10 times. It was 151 times more successful than the shallow baseline.
A 1051x jump. That usually comes from a fundamental algorithmic invention, not just a change in architecture. But here's an interesting part of it. You expect performance to increase smoothly as you add layers, like with llama or stable diffusion. Why didn't we see that predictable curve here?
That's where this critical threshold phenomenon comes in. We observed that performance often stayed flat or saw only minor gains until a specific depth was reached, and then it would suddenly jump.
So it's not a smooth ramp.
Not at all.
No.
On the Ant Big Maze, that breakthrough happened at around 8 layers. But for the incredibly high-dimensional humanoid U maze, the agent needed 64 layers before that dramatic performance increase kicked in.
What's the implication of a threshold like that? Does it suggest that, a certain level of complexity requires a minimum level of representational capacity before a high-level skill can actually form?
That is the leading hypothesis. These emergent skills require a certain minimum depth to synthesize and organize all the necessary building blocks. The capacity has to be there before the model can truly learn the topological structure of the environment or coordinate complex multi-joint movement.
Okay, give us the aha moment examples from those humanoid tasks where the agent has, 21 joints to coordinate?
The difference in the policy is dramatic. The depth 4 humanoid agent, it just failed quickly. It would collapse or just throw its mass haphazardly toward the goal. Very reactive, very low skill.
Right.
Once they reached depth 16, the policies became much more coherent. The agent actually developed the ability to reliably walk upright toward the target.
And just developing bipedal walking is a classic challenge in control systems.
It is. But the truly unexpected, the really emergent behavior occurred at depth 256 in the humanoid U maze, where the agent needs to navigate a wall. Instead of just trying to walk around in a standard way, the deep agent developed these unique, highly specialized maneuvers.
What do they look like?
They were frankly shocking. The agent learned to fold its body forward into this leveraged position to propel itself over obstacles, almost like vaulting.
Boy.
And in other instances, it shifted into a kind of seated posture and literally began to worm its way along the ground to the goal. It was solving the maze in ways the shallow models could never, ever discover through random exploration. These are specialized motor skills that only emerge because of the depth.
That is incredible evidence that depth is creating complexity, not just improving optimization. Okay, let's pivot back to the architecture itself. Prior RL attempts at scaling often focused on network width. How did depth compare to width in this study?
You're right. Prior successful RL scaling was indeed often about width making the layers fatter. This research really asserts that while scaling width does help, scaling depth is generally more impactful, especially in complex state spaces.
Let's use the humanoid environment as the example again, with its 268 observation dimensions. That's a massive state space.
In that exact high-dimensional environment, simply doubling the depth to 8 layers while keeping the width constant significantly outperformed networks that kept the depth shallow at 4 but maxed out the width to 48 layers.
So deep and relatively narrow beat short and wide.
By a lot. And this brings up a crucial efficiency point. If we're aiming for these large-scale models, Memory constraints are always a factor.
Always.
Exactly. The parameter count scales linearly with depth, but it scales quadratically with width. So scaling depth is a far more memory-efficient way to increase the expressive power of the network, especially when you're operating under hardware constraints.
And depth didn't just win its own contest. It also seemed to enable other scaling techniques that had previously failed in RL, like using large batch sizes.
That's a crucial finding that ties right back to representational capacity. Historically, increasing batch size in RL often yielded marginal or even, detrimental results because of the high variance of off-policy data.
Right.
But here, they found that scaling the batch size only became effective when the network depth increased substantially. For instance, it only really worked when depth went from 4 to 64 layers in the humanoid task.
So the shallow network just didn't have the expressive power or the stability to process and make sense of all that high variance information in a large batch. The deep network provides the capacity to absorb that signal.
That's the interpretation. Capacity unlocks utility. And we also saw that, unlike some prior work, this approach benefited from scaling both the actor and the critic jointly. The actor being the policy, the critic being the value estimator.
Interesting.
And while the critic was generally more important, scaling both provided these complementary benefits depending on the environment.
Okay, so if these deeper networks are responsible for such remarkable emergent behavior, the walking, the folding, the worming, what does the internal analysis tell us about what the layers are actually learning?
This is where we see the transition from, let's say, rote memorization to true conceptual understanding. If you look at the visualizations of the Q function in the ant U4 maze.
And as a refresher for everyone, the Q function is estimating the expected return or value of taking an action in a state. It's the core measure of how good a situation is.
Correct. So a shallow depth 4 network computed its Q values based on naive Euclidean proximity. It would show high Q values right next to the maze wall, treating the wall as if it didn't exist. It just assumed a straight line path was possible. It only grasped distance.
So it only learned the map coordinates, not the actual pathways.
Exactly. But the Depth 64 network learned these richer representations that captured the complex maze topology. It correctly showed the high Q values trailing along the required path along the interior edge, acknowledging the barrier. The deep network understands you have to move away from the goal to eventually reach it.
That distinction, Euclidean distance versus topological distance, that shows the depth is learning the rules of the environment itself, not just optimizing a simple metric.
That global understanding is the key. And they proved that this benefit of depth is a synergy between two factors: improved expressivity, so the complexity the network can model, and enhanced exploration, the deep agent's ability to generate better, more informative data.
And you can't have one without the other, can you? A deep model with the world's best capacity is useless if the agent is just collecting poor, low-coverage data.
Precisely. They confirmed this. They took data collected by a shallow, poor explorer and fed it to a deep network. The deep learner struggled. The breakthrough only happens when the deep network's superior expressive power is used to guide its own data collection, generating those unique worming and folding behaviors that provide high-value training samples.
That connects the whole circle between the architecture and the emergent skills. Okay, finally, let's talk about generalization. This is where RL has always struggled. Can these deep networks generalize beyond their training data?
Yes, and this is maybe one of the most powerful findings, shown through something they call partial experience stitching. They train the Ant-U maze agent only on very short, easy start goal pairs, a maximum of 3 units apart.
So they only ever showed it short trips.
Exactly. They make sure the model never saw the long, hard evaluation tasks, which were 6 units apart. They intentionally only taught it short words in the language of navigation.
That's a fantastic analogy.
And the Depth 64 networks excelled at combinatorial generalization. They were able to logically combine those short, easy, partial experiences, those basic words, to solve the challenging, unseen tasks that were twice as long as anything they'd ever experienced before.
That means we're not just learning better policies, we're building models that can compose learned subskills into novel sequences. That is a massive leap for policy generalization in RL.
It's the central conclusion here. Scaling depth in self-supervised RL is the necessary step to achieve compositionality and emergent capabilities, aligning RL breakthroughs with those we've seen in other large AI domains. And let's just reiterate, the shift to the CRL algorithm's classification-based objective is what made this whole architectural scaling stable in the first place.
So what does this all mean for future development? I mean, the obvious limitation we have to acknowledge is the computational cost. Going from depth 4 to depth 24 is expensive.
It is. It increases the wall clock time and computational cost per step, roughly linearly with depth. However, and this is the crucial practical detail, because the scaled CRL models became so much more sample efficient once they hit that critical depth, they often surpass the performance of shallower traditional methods like SAC in less total wall clock time.
So it's an investment that pays for itself in efficiency and eventual success. You spend more compute per step, but you need drastically fewer steps to solve the problem.
A very powerful trade-off.
Now, this entire deep dive has focused on online scaling, where the agent is actively exploring and generating that high-quality data. But the source material noted a sharp limitation. Depth scaling did not seem effective in their preliminary experiments for offline goal-conditioned RL.
Right, where you train solely from a fixed pre-collected data set.
Exactly.
That is the big open question. When you remove the ability to self-generate superior exploration data, the benefits of architectural depth seem to vanish in those initial tests.
Which raises an important question for you, the listener, to consider. We saw that scaling deep networks unlocks this amazing ability to generate high-quality data, the solding, the worming. If that exploration benefit is removed, what architectural or algorithmic innovations are still needed to realize those representational benefits when you're training solely from fixed existing data sets that are often, low coverage or suboptimal?
That challenge of how to utilize deep architecture effectively in the offline setting,
Yeah,
that is absolutely where the next major breakthrough in RL is going to occur.
a fascinating direction for future work indeed. Thanks for diving deep with us. We'll see you next time.